morning, everybody. Roll call. Got the pilot, got the co-pilot, GEOC operator, mission director. All right. Flight mission crew, FCIFs are complete, and flight currencies are all checked. Crew schedule has been published. We're NASA 872. Engine start expecting 0600. Estimated landing of 07 tomorrow morning. So the mission duration is approximately 24.
All right, thanks everybody.
I didn't ignore your email.
First number.
Hawks are strong, powerful birds capable of flying thousands of miles each year. Some species undertake long migrational journeys, a testimony to their strength and stamina. Our bird will fly over 10,000 nautical miles and will reach an altitude of 65,000 feet.
The preparation for an ATTREX flight starts a couple of days before the flight, where we get together and look at the meteorological forecasts and decide where to send the aircraft.
Those targets are determined by the circulation of the atmosphere, which varies from day to day.
So we design a flight based on meteorological data to go down and sample near the tropical tropopause, so what altitude to sample, also what latitude and longitude to sample.
We're looking at all the areas where the scientists want to fly, and we coordinate those areas with the Federal Aviation Administration.
We work with the scientists beginning at that time to come up with options and a plan to get them what they need. We try and maximize the time that we spend in the air.
For this experiment, we're focused on regions where temperatures are cold because we're interested in high altitude clouds. These clouds are about 10 miles or 16 kilometers above the surface.
When all the instruments are ready for flight and everything's been checked out and the aircraft's been checked out, and we button up all the hatches and we're ready for flight.
24 wind calms, out from there 2984.
Once everything is ready in the control room, we give the OK for engine start.
Ground control panel, secure the aircraft to shores.
So we're ready for aircraft taxi.
Copy inward.
Center line, 22 left.
Roger. And Trapper, can I get a takeoff report?
Yes, sir. Runway's clear. You go for takeoff.
Roger that.
40 knots. 80 knots.
Takeoff. Ready now.
Payload admission, this is data, KUS.
We fly it with a mouse and keyboard, and it's more like flying an airline that's always on autopilot.
Well, with the Global Hawk, we have these same controls, only we're just on the ground, and the aircraft could be, several thousand miles away.
Rather than pointing the nose in any given direction or setting a throttle for a particular power setting, we just tell the aircraft, go to this heading, go to this altitude, go to this airspeed. The system itself decides on the best way to get there.
And one of our challenges is to kind of understand the contingency state that the aircraft is in and make sure we understand what the aircraft is doing, and that's what we truly want the aircraft to do.
Most of the time the aircraft is flying in what we call a cruise climb mode. It's actually full throttle in a climb. It gets up to a maximum altitude and then it has to wait to burn fuel off, and as the aircraft gets lighter, it goes a little bit higher and a little bit higher, up to a maximum ceiling of about 65,000 feet.
Coming easy left.
Roger,
and then turn.
One of the things we do during these flights is we have a meteorological team, a team of forecasters down the hall who are watching the satellite products and telling us where thunderstorms are, for example.
There might be colder temperatures south of Hawaii versus just off the coast of South America or Central America. So we have to know where to direct the plane. So we look very carefully at the meteorological situation first. Then when they're in the air and you're flying along, oftentimes these forecasts are wrong.
So when the atmospheric conditions change during the flight, when we're out over the ocean, a lot of times there's a request for us to change our flight track. Maybe the area that they're interested in is in a different area. So one of the things that we will do is coordinate that flight change.
We will use the information we're collecting as we fly along to redirect the plane.
If you'll notice up on that forward deck of the airplane, there's a big white 48-inch dish. That's a KU, a commercial KU SATCOM dish, and that is constantly pointing at the satellite that we have subscribed to for the missions.
We actually get extensive data transmission from what the instruments are measuring in flight.
We decide, based on what we see, to send the aircraft somewhere else or to have it go down to different altitudes.
The classic case, as I said, is you look down, you see a cloud on the LiDAR, and you say, we're going to turn around, descend into that cloud, and sample it.
So we'll profile down through these thin clouds, making measurements of not only water vapor, but the temperature and the pressure, and a range of other gases, including ozone, chlorofluorocarbons, and so forth, so that we can understand the movement of air and the behavior of the air in that layer as we dive down.
One of the great things about this is being that our ground station is building based and we have all of the scientists in the back room. We always fly with two pilots. This gives us the opportunity for one pilot, the mission commander, to get up, go to the back room, leave the other guy to monitor the airplane, and we can talk with any one of the particular scientists, whoever has the most important data that they want to get at that particular time, and we can work directly with that scientist, sit right down at the table with him or her, and decide what's the best way to get them what they want and still meet everybody else's needs.
Obviously, the pilots fly the plane. They're the ones who are talking to ground control, but the pilot has to know where to go, and that's where the scientist's role comes in. The scientist will pick the targets and direct the plane towards the appropriate targets, both before we fly and while we're flying.
It's quite a process because sometimes it can mean a major shift in the flight track. So we will look at what they have proposed and provide some feedback, and then we have to talk to air traffic control to make sure that what we're proposing is okay with them. So we'll change the flight track sometimes many times during a flight.
And so that's how we coordinate between the flight operations team and the payload operations team. So it's a very close collaboration during a flight between both groups.
Very interesting for me too, because coming from a platform where we would just have instruments loaded on the plane and we just go fly a mission, we get real-time interaction with the scientists, and I've learned a whole lot just in the few years I've been doing this on what's going on in the back end of the airplane. Very exciting and very interesting.
872 is coming right, not bad. 30 seconds.
Well, what next and what's important to do?
We hope that ATTREX will improve our understanding of this part of the atmosphere, but ultimately ATTREX will raise some additional questions as well.
We have a lot of work to go, and we hope that doing ATTREX with multiple missions, different times of year, in different parts of, mostly over the Pacific, but into the Indian Ocean, to fully understand the range of conditions that we'll see, that models have to consider all of those ranges of conditions in order to understand the climate system properly.
We need to develop some more instruments and fly them on Global Hawk and other high altitude aircraft to make measurements there as well.
Emily Dickinson once wrote, "The brain is wider than the sky." Many questions have been addressed along the way, and new ones have surfaced. We'll keep searching, for the answer is in the air.